Knowing the orbital energies for the molecular orbitals, which we formed from these linear combinations of atomic orbitals, we can determine the electron configuration of these homonuclear diatomics. So homo meaning the same atom, diatomic, two of them put together. So the way we do this is the same way that we fill in electrons into atomic orbitals, except now we're filling them into molecular orbitals. So we get 2 electrons per orbital. That's the Pauli exclusion principle, because we have to have antisymmetric total wave functions. And that means that we can, that each electron has to have a unique set of quantum numbers. And so we put 2 electrons in each orbital. When we have orbitals that are degenerate, like these pi orbitals, we're going to put 2 electrons with the same spin in each of the orbitals before we start to pair those orbitals. So the way we think about this is we think about, in this case, we're only looking at the valence electrons. So these are row 2 atoms. So their valence electrons are in n equals 2. So we're ignoring the electrons that are in n equals 1. And that means that each lithium brings 1 valence electron to this molecular orbital diagram. So I have 2 electrons total because I have 1 electron from each lithium in the valence orbitals. So I put 2 electrons, and I'm going to start at the lowest energy and put those electrons spin up and spin down. When I move to beryllium, each beryllium brings 2 valence electrons, so I have a total of 4. And so I just build up those electrons by counting the total number of valence electrons that I have in each of these diatomics. So I would write the electron configuration for lithium 2 for diatomic lithium as sigma 2s squared, because I have 2 electrons in there. For beryllium, I would write it as sigma 2s squared, sigma star 2s squared, and so forth and so on. So you can see that we can write these electron configurations just based on the molecular orbitals rather than the atomic orbitals in the same way that we write electron configurations for atoms. So these electron configurations then form the trial wave functions for these diatomics. And then if we want to refine that trial wave function to take into account electron-electron repulsion, we're going to do a Hartree-Fock self-consistent field calculation for the molecular orbitals of the hydrogen ion as our basis set, and minimize that expectation value of the energy to find the best orbital energies for each of these molecular orbitals. In addition to thinking about the electron configurations, we can also determine a bond order for each of these diatomic molecules. So to do this, we want to think about the fact that bonding orbitals add to the bond. So electrons that are in bonding orbitals are helping those atoms bond together. And electrons that are in anti-bonding orbitals take away from bonds. They remove the ability for those atoms to bond. And so we have anti-bonding orbitals that subtract from making a bond. And we have electrons in bonding orbitals that add to making a bond. So remember that it requires 2 electrons to make a bond. So if I take the total number of electrons in bonding orbitals and I subtract the total number of electrons in antibonding orbitals, then I'm going to get the total number of electrons that contribute to bonding. And then if I divide that number by 2, that will tell me the number of bonds or the bond order between the two atoms. So if I look, for instance, at lithium, I can see that I have 2 electrons in a bonding orbital, no electrons in antibonding orbitals, and so the bond order for lithium is going to be 2 minus 0 divided by 2 is 1. And so we actually can form a single bond between 2 lithium atoms to form a single bonded diatomic lithium. However, in beryllium, I can see that I have 2 electrons in a bonding orbital and 2 electrons in an antibonding orbital. And so if I look at that bond order for beryllium, I have 2 bonding minus 2 antibonding divided by 2, because there's 2 electrons for each bond, I get 0. And so that beryllium diatomic doesn't exist. There's no reason for it to exist. There's no bond between those 2 berylliums overall. If I look at boron, then I can see that my bonding and antibonding sigma orbitals that come from the 2s atomic orbitals cancel each other out. But I have 2 electrons in this pi bonding orbital, and 2 electrons make a bond, and so this bond order would be 1. For carbon, I can see that these 2 sigma 2s cancel each other out, but now I have 4 electrons in a bonding orbital, so 4 divided by 2 gives me a bond order of 2 for carbon. And then in nitrogen, I have, again, my 2s are going to cancel each other out. And then if I look at the number of bonding electrons, I have 6. The ones left over after I cancel these guys out. I have 6 bonding electrons. And so the bond order between 2 nitrogens should be a bond order of 3. And that matches with your Lewis structure for nitrogen. Then if I look at oxygen, I can see that, again, the sigma 2s and the sigma star 2s electrons cancel each other out in terms of bonding and antibonding. And now I have 6 bonding minus these 2 antibonding. And so I have 4 bonding electrons overall. And so I have a bond order of 2. And finally, for fluorine, I can see again that these sigma 2s electrons cancel each other out. The pi and pi star electrons cancel each other out because there's 4 bonding here and 4 antibonding here. And I'm left with 2 bonding electrons, and 2 divided by 2 is 1. And so the fluorine bond is a single bond. And again, this matches with what you know when you draw Lewis structures. So oxygen has a double bond, nitrogen has a triple bond, and fluorine has a single bond with 6 non-bonding electrons around each fluorine.